Hi, we're Team Geoforce, and together we are representing the University of Oklahoma. My name is Seth Loggins, and I am currently a PhD candidate in petroleum engineering at OU. My prior work experience is in production and infrastructure engineering. My colleague Zemming is a master's student in petroleum engineering. Zemming's expertise is in subsurface modeling and evaluation. My colleague Ali is a PhD candidate. Ali's background is in drilling and geological engineering. For this year's collegiate competition, we developed a district heating system for Tinker Air Force Base here in Oklahoma City. The system generates an average net heat production of 10 megawatt therms at a levelized cost of heat of $2.70 per MMBTU. Our competitive edge is not only in our experience, but in the institution we represent. The School of Petroleum and Geological Engineering at OU has a rich history of developing engineers, subsurface experts, and innovators. We believe this year's project will have a significant impact, and we are really excited to share our story with you. Here in Oklahoma City, Tinker Air Force Base is the largest single-source employer in the state. The base is one of the largest industrial air bases in the United States, and out of the entire Air Force, it is the fifth largest energy consumer of all bases. The Air Force has committed itself to being a net zero on carbon emissions by 2046. This will require a large effort of all bases, but especially Tinker Air Force Base. The real-world problem we are solving is assisting Tinker with their net zero goals by designing a geothermal district heating system specifically for a facility on base named Tinker Aerospace Complex. The Tinker Aerospace Complex is a 3 million square foot facility used for refurbishing and maintaining various airplanes. Just like the rest of Tinker, alternative energy solutions at the TAC are challenging. Wind is not feasible due to aerial limitations, and a limited land footprint makes solar an unattractive option. The team saw this as a prime opportunity for geothermal. The TAC is located on the south side of the base and currently utilizes natural gas-fired boilers to heat water that is used in a hydronic system. The graph shown here is an annual natural gas energy profile for their boiler system. You can see the gas usage is significantly high in the winter months when Oklahoma tends to have chilly temperatures. This gas is used to heat the water to 125 degrees Fahrenheit for the use of heating the facility. This gas usage can also be seen in terms of energy requirements. The energy rate, or the blue bars shown in the graph, indicate the amount of energy in megawatt therms required from the system annually. During winter, this rate is close to 2 megawatt therms of energy required for heating. The corresponding water rate for this system is represented by the orange line. During winter, to maintain a temperature of 125 degrees Fahrenheit, this rate is approximately 750 gallons per minute, or 26,000 barrels a day. Our goal is to develop a solution to provide enough heat energy to offset the need for natural gas and provide a heated fluid for direct use heating. Our solution is to reuse nearby oil and gas infrastructure to cost-effectively access the subsurface for heat extraction. The team has identified 3 inactive disposal wells approximately 3.5 miles away. These wells are deviated horizontally drilled wells that were originally used to dispose of produced water. They are no longer in operation, but have maintained mechanical integrity to enable safe, efficient access to the subsurface. The nearby oil and gas activity was part of legacy development of the Cherokee platform. All 3 of these wells were drilled and completed in the Arbuckle Formation, which is predominantly of late Cambrian to early Ordovician age. There are many advantages to reusing these wells. One is that these wells have the deepest true vertical depth in the immediate area around Tinker, with an average true vertical depth of 11,500 feet. The deeper the access, the higher the temperature access. Secondly, all 3 wells have large production casing. This casing enables downhole access for operations such as tieback strings, size availability for re-drills, efficient hydraulics, and downhole pump and tool operations. Bigger holes are always better. Lastly, they are all located on one pad site. This allows for streamlining operations at the surface and mitigating risk. All in all, the estimated downhole temp of these wells are 220 degrees Fahrenheit, or around 105 degrees C. These temperatures are based on gradient maps as well as direct wellhead measurements. To quantify the resource potential of these wells, we conducted an enthalpy sensitivity assessment for several variables related to the subsurface model. This allowed us to analyze 23 different solutions for our enthalpy production. Once we gathered this information, we were able to generate a heat type curve based on all 23 enthalpy solutions. This solution on a net basis shows the average heat production for the system to be 10 megawatt therms. This curve would serve as the basis of our district heating design. To capture the heat energy and deliver it to our end user, our engineering system design involved 2 wells to be injectors and 1 well as a producer. We would bring this fluid to surface via an electrical submersible pump. Once at the surface, we would transfer this heat energy to the working fluid used in Tinker's facility via a plate heat exchanger. After transferring the heat energy to the working fluid, the produced fluid would then be re-injected downhole to preserve reservoir pressure, regenerate heat flow, and eliminate the need for disposal. After the working fluid is heated in the exchanger, the fluid would then be piped to Tinker Air Force Base for the use in facility heating. Once depleted, the working fluid would then be pumped back to the well site to gain energy with the produced fluid once again. Aside from the heat exchanger and pumps, the primary design and cost consideration was the pipeline. The pipeline chosen for this project was a composite pipe material named Flex Steel Pipe. The advantages of this pipe include a corrosion and erosion resistant HDPE liner that is strengthened by an inner steel component. This pipe offered the added pressure capacity required for pumping the needed volume, while still allowing for corrosion resistant properties in the needed temperature range. As opposed to HDPE, which did not meet our pressure requirement, or steel, which would be costly, Flex Steel provided the combined solution of the 2 materials. Working with industry experts, contractors, and pipeline service companies, we determined the total capital investment required for this project to be $2.6 million, along with an annual cost of $750,000 million for operational expenses. Using these estimated costs and the total energy production from the wells over 30 years, we estimated the levelized cost of heat for this project to be $2.70 per million BTUs. This is highly competitive with natural gas. As seen over the last 10 years, the Henry Hub gas spot rate has averaged $3.35 per million BTUs. The benefit of this project is not only to deliver consistent energy, but deliver consistent energy at a consistent price. Our solution is transformational because it is a cost-effective, minimum footprint, clean energy solution that enables energy security for Tinker Air Force Base and the nearby area. The project generates more energy than what is required from the TAC, allowing Tinker to consume additional energy and still have excess for other facilities nearby. These places include industrial businesses, schools, and communities, all located within a mile radius of the district heating system. Along with Tinker Air Force Base, our team was able to raise awareness of the impact of geothermal energy to a group of students at the Gordon Cooper Technology Center. The Gordon Cooper Technology Center is a public career and technology educational center that trains students in various STEM fields. We were able to spend the day with the students and teach them about geothermal energy, talk about how it can be used, and how it can impact their lives. More importantly, we discussed the need for future engineers and scientists, just like themselves, to help progress geothermal energy. We had a great time, and we were invited back to participate in a special lecture once a semester where we get to continue our outreach and talk about geothermal energy. Our team is very grateful for this opportunity, and we're more excited to see this project take action. We would like to send a special thanks to Tinker Air Force Base, our service companies, University of Oklahoma, and everyone else involved in this project. We couldn't have done it without you. We hope you enjoyed, and thanks for listening.